Okay, so sorry about that. So what I'm trying to say is that psi is an eigenvalue, eigenfunction of, or an eigenvector of m dagger m, right? So if psi is an eigen, so what we can do is that we can now multiply this equation on the left by psi dagger. So we have psi dagger, m of psi is equal to, but what is this? This is nothing but psi prime. And what is this? This is nothing but psi prime dagger. And this object is positive or zero. And so we get that from this equation, this equation also means we have C psi dagger psi, that is greater than zero. Obviously, this is, we're assuming this to be non-zero. So that means that, well, we're assuming this to be not just non-zero, positive, right? So this means that C is zero or positive. Right? So thus we have seen that any operator which has this form has eigenvalue positive, right? Positive definite eigenvalue. Has positive definite eigenvalues. Okay, is that clear? Okay, so now let's get back to our original guy, which is rho squared. Now let's define a vector E, J. So this is a label, the J is a label, but its kth element is given by delta JK. So essentially it's a vector. Say E3 is a vector whose just third element is zero, okay? Let us define these vectors. Okay, now let's look at rho squared. Now rho squared is by definition, it's what kind of matrix is it? Can you remind me?
Diagonal.
Exactly. So the only element I care about are the I element, no sum. There's no sum over I. I is repeated, but there is no sum here, okay? So this thing is going to be the same thing as EI dagger rho squared EI, right? Okay. Do you agree?
That's just the basis, writing it in the basis, right?
Yeah, it's some sort of orthogonal basis, yeah. But this is a triviality, if you like, because if you take rho squared to be, say, if you take the LK element of rho squared and you say, okay, I'm gonna multiply this by EI, and then you have to have L, sum over L, and then EI, and sum over K. There's no sum over I. So the sum is over L and K, right? And then if you introduce the delta here, right, then you just get these two indices to be the same, right? So that means, so yeah, this is kind of a very trivial statement. So after that, what we write is G EI dagger W dagger D tilde dagger D. Here, remind you that this is what depends on G, D tilde. Then there's W and EI, right? I've just written out the definition of rho squared. But you see that this thing is some vector psi phi I, and this thing is some guy phi I dagger. Okay, so each of these terms is positive definite, and therefore the sum is also positive definite. Okay, so this shows that the eigenvalues of the eigenvalues of rho squared are positive definite. So then let's define another matrix, which is just the square root of rho. And then define D of G to be a matrix such that it's rho times the unitary matrix W dagger, the non-unitary representation D tilde, then W rho inverse. Okay, we're assuming that rho inverse exists, and you can show that it does exist. Okay, so this matrix I'm going to claim is a unitary matrix. And this is the unitary representation that we were looking for. So D dagger of G is then going to be rho inverse dagger, W dagger, D tilde dagger of G, W rho dagger. Okay? But we know that rho is a Hermitian matrix, right? Because it's a diagonal version of H. Therefore, we can drop that and W dagger, D tilde dagger, W rho. So this is the expression for D dagger, and this is D. And now let us compute let us compute D dagger of G and D of G. And this is just now a very boring thing, but let's do that.
Sorry,
D dagger.
is the square root of a diagonal matrix always diagonal, by which?
Yes. Yeah. It's always diagonal. Yeah. If the fifth diagonal entry is 5, the diagonal matrix has this. Okay. But we're taking a positive, or I don't really care about that. Okay. Okay, so rho inverse. So it has rho inverse W dagger D tilde dagger W rho. And then we have D, but D has at the beginning another rho. So we have here rho squared. And then we have W dagger D tilde, then we have W rho inverse. Okay. Now, what we can do is we can then use the definition of rho squared. The definition of rho squared is W dagger H of W, right? So, and then we have W dagger D tilde W rho inverse. So this is 1. And this is 1. So we have rho inverse W dagger D tilde dagger H D tilde W rho inverse. But this thing is invariant, and this thing is H. So we have rho inverse W dagger H W rho inverse. But this thing is nothing but rho squared. So we get rho inverse rho squared rho inverse, and therefore we get 1. And therefore we have shown that D, as we constructed, D dagger D is 1. And therefore this thing is a unitary representation of our finite group. And by extension, by replacing all the sum by integrals we get, we get the same result for compact Lie groups. Okay, now just a corollary, or just a comment, I should say. Comment is that we have to assume the determinant of rho is non-zero, because otherwise, if I go to rho squared, where is rho squared? Here. So if I go to rho squared and I assume that its determinant is not zero, that would imply, you can show that that would imply that the determinant of d tilde is zero. And that's, of course, not true, because otherwise it would not be a group. Because for group, we have to have inverse elements. Okay, so this was the proof of the unitarity theorem. Any questions?
Sir, so what, I mean, the idea, what was it basically like what we basically found, like rho square first, and I mean, I'm a bit confused about the idea that why we came up with this particular presentation, how we did so.
Right. So the idea is that it's a proof by construction. That you will always find proof by constructions in mathematics, and the idea is that if I give you, I call you into my office, now here I have constructed a non-unitary representation of some compact Lie group. But because I'm a physicist, I want to apply it to some physical system, but I need a finite dimensional, the same dimension, but I need the same finite dimensional representation of the same Lie group, but it has to be unitary. Otherwise, my lab cannot use it on my quantum system. Right? That's a very real life scenario. So I give you this all these matrices, which I have proved to be a unitary representation of the finite dimensional non-unitary representation of a group. And you have to find a unitary representation. This proof gives you an algorithm for that. Okay, this proof tells you that if you construct these D matrices in this manner, okay, so then the resulting object is going to be unitary, and because I have not shown that this is a representation, right? But you can show that, right? You can show that this is a representation using the fact that this is a representation. Because you can see that this rho inverse is going to, if you say, okay, yeah, they cancel. So it's almost obvious. Yeah. Okay. So I'm not sure how.
Sir, I am confused about the first line you wrote, that in proof, like we use the rearrangement lemma. Suppose there exists a non-unitary representation of G given by d tilde G. So
yeah.
like, where is that non-unitary representation?
Oh, it's given. Yeah, that's given. We are assuming that there is a non-unitary representation.
So we eventually like converted from this induced a unitary representation from this non-unitary representation.
Exactly. We basically constructed a unitary representation from a non-unitary representation.
Oh, I see.
Okay. Very good.
Is it not possible for there to be a no non-unitary representation?
Yeah, of course. I mean, you can have non-unitary representation. It's actually, I think, for compact Yeah, I mean, yeah, of course. Like, for example, many, I mean, I don't know.
I might have worded my question wrong. Isn't it possible that we don't have a non-unitary representation?
If you don't have a non-unitary representation, then you have a unitary representation, right? It's an either-or thing.
So you have to have at least one representation for a group.
Yeah, if you don't, I mean, for example, a group must have a defined, like if you have a Lie group, if you have a matrix Lie group, it has at least a finite, it has a defining representation, right?
Oh, I see, yeah.
And you just work with that and you say that, oh, this is non-unitary. What do I do? But it's compact. You just follow this algorithm and you construct a unitary representation.
I see.
Okay. Okay.